Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hello students, good morning. In our last class, as you know, we studied about the purification of colloids, and the purification of colloids is what is the process of reducing the amount of impurities to a requisite minimum level is called the purification of colloidal solution. And this purification we have seen we can do using dialysis or the electrodialysis or by ultrafiltration. And this, what we know, the dialysis is done using a membrane, and this membrane could be parchment paper, cellophane sheet, or animal membranes. And these membranes allows only for certain small ions or small molecules to pass through. It doesn't allow colloidal particles to pass through it, and so colloidal particles will remain be inside the solution or in the membrane, and the other small ions and the molecules will go out. And this was one figure that we have seen earlier. And so the colloidal particles will be large in size, they will not pass through this membrane, only a small ions can pass through, and thus one can purify this colloidal solution. And this apparatus is called dialyzer. Then, as we know, we have seen that this process is very slow. To expedite this process, we use electric field. So we add two electrodes in this compartment, and using these electrodes, once you will create a potential difference between them, an electric field will be created, and under this electric field, the different ions of the electrolyte will move to the opposite electrodes. So then, if the anion, if it is anionic, it will move towards the anode, and if it is cationic, it will move towards the cathode. A force will be created. A force will be exerted by the electric field on those charged particles, and so the process will become faster. And then we saw the ultrafiltration. Ultrafiltration we do use ultrafilter papers, and ultrafilter papers are the or you make one can make by using ordinary filter papers. Usually, ordinary filter papers do not stop colloidal particles, even colloidal particles, to move through. So what we do, we try to reduce the pore size of this ordinary filter papers, and that we do by using a collodion solution. And using collodion solutions, one can, and then after then making it hard using formaldehyde, and so we can do this kind of ultrafiltration. So we can create ultrafilter papers, and using ultrafilter papers, one can also purify the colloidal solutions. But again, this process is slow, and but then this process can be expedited by applying pressure on the salt side, as you can see here, pressure on the salt side, this is salt side, or by applying suction on the filtered side. Maybe one can apply suction in this side, and so this process of ultrafiltration will become faster. Then we saw properties of the colloidal solutions, and this is what we are going to finish today. So some of the properties we have seen. So the colloidal solution are heterogeneous. The dispersed phase or the dispersed particles cannot be seen through naked eyes. The colloidal particles cannot pass through ordinary membranes. This is the filtrability, and the colloidal particles are usually stable. And then, and we saw the colligative properties. So what we have seen about the colligative properties, the particle size is in the colloids are larger. So many small molecules they aggregate together to form a how to form one colloidal particle. And thus, if you look at the corresponding number of particles into the pure solutions where the solutes are dissociated into the molecules or the ionic forms. So solutes are in the form of ions or the molecules into the pure solution. However, these ions and molecules they get form aggregate in the colloidal solution. So the number of particles, if you look with the same amount of or same number of moles of the uh, colloidal solution and the same number of moles of solute if it contains by a true solution, and if the volume is also the same, so what you see, the number of particles in the true solution will be more, and thus the colligative property in the two for the two solutions will be higher. Then we show the Tyndall effect. The Tyndall effect was usually when a light is passed through the colloidal solution, we can see the path of this light, and that is what we call the Tyndall effect. And this Tyndall effect is used to uh, differentiate between true solution and the colloidal solution. So in true solutions, you cannot see the path of this light source, the light which is passing through the transmitted light. You cannot see the path of the transmitted light. However, in the colloidal solution, you can see it, and this is because in the colloidal solution disperse the light. It absorbs the light and then scatter it in different directions. So that because of the scattering of light, we see the path of the colloidal solution. Some examples we have already seen, like we can see the path of such light beams. This is because of the small colloidal particles that are there into the air, and the Tyndall effect is due to the effect of colloidal particles and the scattering of light. This thing we have already seen. The two important conditions that should be satisfied mm, uh, for the Tyndall effect is what is the diameter of the dispersed particle be a small, should not be much smaller than the wavelength of the light source or the light beam that is used. And another thing is the refractive indices of the dispersed phase and the dispersion medium should be large. So difference in the refractive index which is large. So then one can see with the denser and rarer medium, this kind of things wants to understand. Then if there is a clear difference, then only we can see the Tyndall effect. And then we see the Tyndall effect usually this ultra microscope designed by Zsigmondy. And this ultra microscope, using ultra microscope, one can differentiate between true solutions and the colloidal solutions. And there, when you see using this ultra microscope here, you see the colloidal particles. It appears like a star in a dark background. And so one can say this is the colloidal solution. If you do not see these kind of things, which means it's a true solution. Then we show the color of the colloidal solutions and the color of the colloidal solution. About this, we have seen the color of solution depends on the wavelength of light that is scattered by the dispersed phase of the dispersed particle. So whatever the wavelength of the light that is scattered, so light is absorbed by the dispersed phase particle, then it is scattered and scattered. The wavelength of the scattered light actually decides what would be the color that we perceive for the colloidal particles. And that's the one thing. And so this color, this what is the wavelength of this scattered light, it depends on the size of the colloidal particle. This is what we have also seen, and depends on the size of the colloidal particle. So what we see usually, if the size of the colloidal particles increases, we see the color of the colloidal solution changes. For example, if you see, start with the finest gold salt, and to make it coarse, gradually what we see, the color of the solution changes from red, become purple, then blue, and then finally it becomes golden. So you can see the change in color at different size of the colloidal gold particles. Then the color of the colloidal solution also depends on the how the observer receives the light. And observer receives the light means the observer is receiving the reflected light or the transmitted light. What kind of light the observer is observing, depending on that also the color of the colloidal solution changes. And for example, if the mixture of milk and water is seen, and if it is seen through the reflected light, it appears blue, and when this mixture of milk and water it is seen through the transmitted light or viewed by the transmitted light, it appears red. And so one can see whether you are seeing the colloidal solution by the reflected rays or by the transmitted rays. Transmitted rays, for example, here in this mixture of water and milk, we have seen transmitted rays. If you see this solution in the transmitted rays, it will appear red, and if you see the solution by the reflected rays, it will appear blue. And so on. We also see how the observer receives the light. Depending on that, also the color of colloidal solution changes, and we perceive different colors of the colloidal solution. Then we show the Brownian movement, and Brownian colloidal particles are in continuous random motion, and that we call the Brownian motion. And we have also seen the Brownian motion is mostly due to the collision of the particles of the dispersion medium with the colloidal particles, and that is the particles of the dispersed phase. And we have also seen this motion depends mostly on the two uh, things, two properties, two phenomena, and that is the size of the particle and the viscosity of the medium or the colloidal solution. And if this viscosity is larger, this motion will be slower, that we understand. And also there is the particle size, the particle of the colloidal the colloidal particles are larger in size, and also this motion will be slow. And then we show finally the charge on the colloidal particles, and this is what we will be completing, and we'll see some other properties of the colloidal solutions as well. And what we have seen in our last class, that the colloidal particles do carry certain charges. The charges may be positive or the negative charge. If in the colloidal solution all the particles have the charge of the same nature, means if the particles are negatively charged, all the colloidal particles will be of negatively charged, and if the particle of the colloidal solution is positively charged, all the particles will be positively charged. And because of this repulsion between the same charged particles of same nature, the colloidal solution gets stability. And we also saw some based on that this charge on the colloidal particles. Colloid may also be divided into the negatively charged colloid and positively charged colloids. And the examples of negatively charged colloids are metal sulfides and metal dispersion. And then we also see the acidic dyes and so on. The positively charged colloids are metal hydrides or hydrated metal oxides. You can say the same thing. Then basic dyes or the metal oxides are positively charged colloids. This is seen, and then finally what we saw is the charge on the salt particles may be due to the following regions, and these are the regions because of which we see the charge on the colloidal particles, and the charge again may be positive or the negative. Another one reason is the electron captured by salt particles during electron dispersion of metals. The electron dispersion of metals, while doing this, the particles also capture certain electrons, and because of that they get negatively charged. Then preferential absorption of ions from the solution, and these colloidal particles they also absorb certain ions preferentially. They may absorb positive ion or the negative ion. If they absorb positive ions, the colloidal particles will become positive, and if they absorb negative ions from the solution, and these ions still they are in solution, means they are in excess, and they so mm, mm, the charged particle, if it absorbs negative charge, it will become negatively charged, and then also the formulation of the electrical double layer. These things we will elaborate in a detail today. And also some colloidal particles develop electrical charge due to the dissociation or ionization of the surface molecules. For example, that we have seen for the soaps and detergents. Soaps and detergents are the soaps, they are actually the sodium and potassium salts of soaps are sodium or potassium salts of fatty acids. And if they are salts, it means they are electrically neutral. They have cations and anions. And but what we see when they form the colloidal particles, the colloidal aggregates, the associate, and that we see in the form of micelle, the charged particles should be on the surface of the micelle. But this charged particle is only the anion appears there, the cation goes into the solution, and that happens because of the dissociation of the cation from the anion at the surface of the colloidal particles. And so with these colloidal particles like micelles, they get certain charges, they uh, acquire certain charges because of the dissociation or ionization of the surface molecules. And these things we already know. So the cations, for example, in this case, sodium palmitate is one of the soap. The cations pass into the solution while the anion, this one part tend to form aggregates above critical micellar concentration due to weak attractive forces present in the hydrocarbon chain. And this weak attractive intermolecular forces are nothing but they are dispersion forces, or sometimes some books also reports the van der Waals interaction. So the charge on colloidal particles due to selective absorption of ions, this is this point that we are going to see, preferential absorption of ions from the solution, and because of which also from the some colloidal solution gets charged. So when two or more ions are present in the dispersion medium, preferential absorption of ions common to the colloidal particles usually take place. What does it mean? Suppose a colloidal particle is also made up of ions, and if it is made up of ions, the solution contains what ion of these colloidal particles, and depending on that, and if what ion it contains, the solution contains, the same ion will be absorbed by the colloidal particles. For example, if you look at the highly diluted solution of silver nitrate, when it is added to highly diluted Ki solution. So Ki solution is already there. So potassium and iodide ions are in excess. You know Ki is dissociated into corresponding ions in aqueous solution. Now you are adding AgNO3. So as soon as you are adding AgNO3, each Ag plus AgNO3 is also ionized, almost 100% ionized. So Ag plus and NO3 ions will be separated out into the solution. Now this Ag ion will go and combine with iodide ion to form precipitate of AgI. And this AgI precipitate of the AgI will form the colloidal particles. And now this AgI forms the colloidal particles. So colloidal particle is made up of Ag and I ions, iodide ions. And the iodide ion and Ag ion of the solution already contains Ki. Ki means potassium ion and iodide ion. So the what ion is common in the to the colloidal particles in the solution, it is iodide ion. So in that case, iodide ion will be absorbed by the by AgI, silver iodide, and so the iodide ion will be absorbed. It means the colloidal particles will become negatively charged. So when highly diluted solution of silver nitrate is added to highly diluted Ki solution, the precipitated silver iodide absorbs iodide ions from the dispersion medium and negatively charged colloidal salts results. So negatively charged because iodide ion is absorbed from the dispersion medium. Dispersion medium also contains water, which also contains soluble ions. So the soluble ions, they will absorb the ion which is common. So AgI, what AgI contains Ag and I ions, and what ion is common into the solution? It is K and I. So common ion is I. So iodide will be absorbed, and this is what it means. The preferential absorption of ions common to the colloidal particles usually take place. The preferential absorption that is common, the iodide is common to the colloidal particle which contains Ag ion and I ion. The red ion is absorbed in this case. And so note here that Ki is in excess at this stage and iodide is being common to AgI. However, when you add Ki to the AgNO3 solution, so in AgNO3 solution, you are adding Ki slowly. It means AgNO3 is already in excess. So Ag ion and NO3 ions are already in excess. As soon as you add Ki, AgI ions of and the colloidal particles will be formed. Colloidal particles of AgI silver iodide will be formed. And now these particles see some common ion in the form of Ag plus ions in excess into the solution, and so it will absorb Ag plus ions. And these colloidal particles in this case will absorb Ag plus ions, and thus the colloidal particles will carry positive charge in this case. So what we see when Ki solution is added to AgNO3 solution, positively charged salt particles due to absorption of Ag plus ions from dispersion medium. So it results due to a positively charged salt results due to absorption of Ag plus ions from dispersion medium. And so in first case, this case, what we see is the formation of AgI, then iodide ions are absorbed. So this colloidal particle is negatively charged. And in the second case, when Ki solution is added to AgNO3, the colloidal particles of AgI absorb Ag plus ions from the solution and thus positively charged colloid results. Similarly, if you see the formation of AgCl, suppose AgCl is there in the form of the colloidal particles and the solution contains chloride ion in excess, means the dispersion medium contains chloride ions in excess. So the chloride ion will be absorbed by AgCl. And so preferential absorption of chloride ions, which called thus the colloidal particles require negative charge, so AgCl and the chloride ion. However, the colloidal particles contains which are AgCl colloidal particles, it has no charge. And if silver ions present in excess into the solution, Ag plus ions and Ag plus ion is common to this. If the cation K plus ion is there, K plus ion will not be absorbed by this. It will absorb only those ions which are common to the colloidal particles, Ag plus ion. And that is why in the previous case also here we do not see the absorption of K plus. K plus is not absorbed or the NO3 nitrate ion is not absorbed to form negatively charged colloidal particles, or potassium ion is not absorbed to form colloidal positively charged colloidal particles. Ions which is common to the colloidal particles are only absorbed. So here in this case also, even if there are other cations that are there, but those cations will not be adsorbed by the AgCl colloidal particles. Only Ag plus ions will be adsorbed to form positively charged colloidal particles. At this we call a preferential adsorption. If you look at the another example, so FeCl3 when it is added to excess hot water, so it forms FeOH thrice, or the one we also call ferric hydrated ferric oxide salt particles or the colloidal particles. So these particles when it is added to hot water, so hot water it forms hydroxide, but how these OH minus ions they are very less in amount in the that neutral pH and in the form of water, and thus these OH minus ions are not there. So what will be excess? So few of the Fe plus ions, Fe3 plus ions will be absorbed by a ferric hydroxide salt particles, and thus it will absorb Fe plus ion, 3 plus ions, and so the colloidal particles will be positively charged in that case. So if FeCl3 is added to excess of hot water, a positively charged salt of the hydrated ferric oxide is formed due to adsorption of Fe3 plus ions, iron 3 plus ions, and thus a positively charged salt is obtained. However, when ferric chloride is added to NaOH solution, now ferric chloride is added to NaOH solution, means the solution also contains OH minus ions, of course it also contains water. So it will form ferric hydroxide. Along with the ferric hydroxide, what we see OH minus ion is in excess, and OH ion is common to the colloidal particles. Fe ion or OH minus ions are common. So in this case, OH minus ions will be absorbed by the colloidal particles, and so negatively charged colloid will result due to adsorption of OH minus ions, which is common to the ion that is there in the colloidal particles. This is effectively FeOH thrice. So having acquired a positive or negative charge by selective adsorption on the surface of colloidal particles, so we have seen this, the selective adsorption of colloidal particles happens, and since it is adsorption, so this adsorption will happen, so ions, the positively or negatively charged ions will stay only at the surface of the particles, it will not go inside. If it will go inside, then it will be absorption. So since it is absorption, so these ions are adsorbed onto the surface of the colloidal particles, and depending on that we see the colloidal particle, and thus particles this layer attracts counter ions, and when since they contain these surfaces contain certain charge, and now because of the adsorption of these particles, these ions, so they attract counter ions from the solution. And so if this is negatively charged, suppose AgI, and then I minus is the negatively charged salt particle or the colloidal particles is there, so it may absorb K plus ions from the solution. In this case that we have seen, because this solution also contains K plus ions. And now this K plus ion behaves as a counter ion. This counter ion is because the iodide ion is here, so the counter ion is the cation, so it will absorb counter ion here. If the sol is positively charged, it will attract negatively charged ion, and that is I minus ion, which may absorb. And thus the combination of two layers of opposite charges around the colloidal particle is called Helmholtz electrical double layer. And thus what we see the formation of two layers, positive and negative layers, usually these layers are called Helmholtz double layer. The electrical double layer, if you look at the electrical double layer, later on people have done this. Other than Helmholtz, people have also seen many other things. The Stern and other people have done research, and they say that the first layer, there are two layers, the electrical double layer formation happens. So electric double layer, suppose this is the colloidal particle, and this colloidal particles of AgI, it absorbs iodide minus ions at the surface. So these ions, the iodide ions, negative ions will attract counter ion K plus from the dispersion medium, and so the K plus ions will come and they will be in close contact with this I minus ions. And because of this close contact and they are very near to each other, they get very strongly associated because of the electrostatic interaction. And so this interaction, this K plus ions, they forms a fixed layer. So they get closely or very strongly associated to this layer of the colloidal particles which contain certain ions of negatively charged. And if it was positively charged, so the negatively charged ion will be there on the next layer. And this layer, it is unmovable, and thus it is called the fixed layer. So this is the fixed layer. One layer is this fixed layer, and another layer, and this fixed layer, the which is also called a Stern layer, it contains counter ion, this counter ion to this ion. However, these counter ions are not able to neutralize overall this thing, so some more ions will be added in the nearby and in the surrounding, and these ions however also contain some ions of the like charges, but these ions contains counter ions in more concentration. So this ion also contains K plus ion in a higher concentration. And this ion, this layer, actually this layer is called the diffuse layer. So there are two layers. One is the external layer or the fixed layer, and another is diffuse layer. External layer or fixed layer is fixed; its position is fixed. However, there is another layer which also required for the electrical neutrality of this entire particle, and thus this we call the diffuse layer. The net charge, if you look at the end of the diffuse layer, will be zero, so the potential will be zero at the end of the diffuse layer. However, if you go inside, you will get certain negative potential in this case, and if the colloidal particle contain positive charge, positive potential there. So thus the anelectric, the first layer of the ions is firmly held and is termed fixed layer or external layer, while the second layer is mobile, termed diffuse layer. And this that is why this mobile, it is diffuse layer, and the diffuse layer also contains some particles of the dispersion medium, some ions as well, and some molecules of the solution as well, and the ions as well. So an electric double layer is a surrounding a particle of the dispersed phase. So an electrical double layer is a layer surrounding a particle of the dispersed phase, including the ions absorbed on the particle surface and a film of the counter charge dispersion medium. And the counter film of counter charge dispersion medium is another layer, and this is what this layer. So this also contains this counter charge. This has the negative, and it also contains some of the molecules of the solution as well. So this is counter charge dispersion medium. So these are two layers that are formed. So this is diffuse layer. The electric double layer consists of three parts. So the electric double layer overall, when we see, it consists of three parts. One is the surface charge. This is the surface charge, and the charge ion absorbed on the particle surface. Another is called a external layer, and this is the external layer. And this external layer is the counter ions attached to the particle surface and closely attached to it by electrostatic force. So this external layer contains counter ions, and the counter ions to the particle, the charge that are there on the colloidal surface, and these ions are closely or very strongly associated to this surface of the colloidal particles due to a strong electrostatic interaction. And then the third layer is the diffuse layer, and this diffuse layer contains free ions with a higher concentration of counter ions. So it contains free ions. These ions are not fixed, and the counter, it must is the concentration of the counter ions when the ions opposite to that uh, is there on the surface of the colloidal particles. So the ion opposite to that is the concentration is more in the diffuse layer as well. The ions of the diffuse layer are affected by electrostatic force of charged particles, and thus they are affected by the electrostatic force of the charged particles. The electrical potential within the electrical double layer has a maximum value on the particle surface. As you can see, the magnitude of the electric potential will be maximum at the particle surface, and as we go away from this, what we are seeing the addition of the counter ions, and because of the counter ions, we see less charge, amount of charge is enclosed here, the net charge is enclosed here, so the potential will start decreasing. And at the end of the diffuse layer, the mm, potential will be zero, and it is maximum at the particle surface. The potential drops with increase of distance from the surface and becomes zero at the double layer. And so what we see, the potential drops with increase of distance from the surface, and this is what the surface having highest potential is the highest negative potential, and as we go away from the surface, as we go away, this negative potential it drops, and drops, it becomes zero at the end of the diffuse layer. You can see here, and then this layer, at the external layer, there is some also some negative potential. It means this negative charge on this particle is in excess than the charge that are there into the external layer. And so there is still certain negative potential in this case. And further we look at this potential, there is the one plane that is called the sleeping plane or the shear plane or or it is also called hydrodynamic plane of shear. And at this plane the potential is called the zeta potential. This zeta potential we see. So what is this potential difference? So when a colloidal particles moves into the dispersion medium and these particles are there, and as we know that colloidal particles they are not fixed at a position, they move into the colloidal solution or the motion, that the Brownian motion that we have seen. But when these particles move, a layer of the surrounding liquid remains attached to the particle. A layer of the surrounding liquid that is remains attached to this particle. Also there is some movement or diffusion that may happen between the particles, and that layer is called the sleeping plane, and the boundary of this layer is called the sleeping plane. This is the layer which moves along with the colloidal particles, and that thin layer is the boundary of this layer is called the sleeping plane, and the potential at the sleeping plane is called the zeta potential. So when you measure the potential at the sleeping plane, is that potential is the zeta potential. The electric potential value at the sleeping plane is called zeta potential, and which is a crucial parameter in the theory of interaction of colloidal particles. So the theory of colloidal particles, which is not in our syllabus, this zeta potential has a crucial meaning, it has crucial significance, and so zeta potential must be remembered and understood. One can also understand the zeta potential in terms of like that we see the formation of the capacitors. So what we see, there is a net charge using these two layers, and that one can consider this one as layer, fixed layer with these particles as one plate, and another plate will be this with the diffuse layer. And thus what we see, there are two plates with the different electric charges, and two plates having different electric charges will be having some difference in electric potential, different electric potential. And if there is a difference in electric potential, there will be electric field between them, and thus the potential, whatever the difference in the potential between two mm, layers that you see, which behaves like two plates of capacitor, is called the zeta potential. So the charges of opposite signs on the fixed and diffuse part of the double layer results in a difference in potential between them in a manner similar to the potential difference developed in a capacitor. And the capacitors, what they have two plates and they have different charges, and because they have different charges, so their potential difference is created between them, and thus we see that potential is there into the capacitors. Here we also see this behaves like a capacitor, and this potential difference between two layers, fixed layer and a diffuse layer, of opposite charges. The fixed layer contains usually negatively charged particles in more concentration. So net negative charge will be there on the fixed layer up to here, and the diffuse layer will have, in this case of example, this example where the colloidal particles are negatively charged, and diffuse layer will have more concentration of positively charged particles, so they will be positively charged, and so the opposite they will have opposite charges, and so there will be electrodynamic potential, and this potential is called electrokinetic potential or zeta potential. So this potential is electrokinetic potential called electrokinetic, and the zeta potential, and these things we have already seen. One can see this figure again in this case. So this is the colloidal particle having, although it is shown only three charges because this is particle and three dimensional, what we see there is a number of more number of negative charge in this case, and so this is the stern layer or the fixed layer of the opposite charge of the counter ions. Still what we see up to here, there is a net negative charge in this case, and the potential at here at the surface of the colloidal particles, which we call the surface potential. So surface potential is what? Is the potential at the surface of the colloidal particles, and the surface of this colloidal particles also contains certain absorbed ions, because of which these surfaces are having certain type of charge, whether positive or negative. And now the adsorbed ions, and that adsorbed ions in the first layer, the stern layer or the fixed layer, and the potential at this point is called stern potential. The stern potential here it is also defined. Stern potential means the potential at the surface of the stern layer is called stern potential, and the potential at the surface of this hydrodynamic plane of shear or the slipping plane is called zeta potential. And still, even though it is zeta potential, but this doesn't mean the diffuse layer ends here. Diffuse layer even goes further away from this, as you can see here. And so the diffuse layer, at the end of diffuse layer, we see the potential become zero. And this stern layer is what the particle will attract ions of the opposite charge, and this is what we see on stern layer or the fixed layer. And the particle will, this colloidal particle will attract ions of the opposite charge. Positive ions will move closer to the surface. These ions are tightly bound immediately around the surface. The hydrodynamic plane of shear is the charges beyond this slipping plane will not move with the particles as an entity, but all the charges which are within this hydrodynamic plane, that they will this boundary, within this boundary will move with the colloidal particle, and this plane is, and within this boundary will move with the particles as one entity, and this is what this plane is called, the hydrodynamic plane or the shear plane or the slipping plane. And the diffuse layer, ions are diffused in the diffuse layer more freely around the particle, and so these particles move more freely. So if two particles of an insoluble material do not have double layers, so this means the precipitate. So if two particles of an insoluble material, means colloidal particle, if they do not have a double layer, they can come close enough and attractive van der Waals forces pull them together. So what happens if there is no electrical double layer? So these particles can move closer because this double layer formation, and this in this example, when the colloidal particles contains negative charge, so the diffuse layer will have excess of positive charge. And so because of the excess of positive charge, even at the larger distances, there will be repulsion. And also what we see, these particles is here, and distance between two particles will increase because of this diffuse layer, because these colloidal particles with a double layer, they cannot move closer than this layer, and if they don't move closer to this layer, the distance between these two particles will be more, and so the short range forces, relatively shorter range forces, will not be in effect like the dispersion forces, although they are also considered long range forces, but they are relatively much shorter range than the electrostatic forces. And so the electrostatic forces in the repulsion, because of the diffuse layer, will start working even at the larger distances. And the dispersion forces, their interaction is, means their nature is always attractive interaction, is attractive. So these attractive forces will start working when the particles will come closer to a certain distance. But these particles cannot come closer because of the formation of the electrical double layer. And once they become closer after a certain distance, then only the attractive dispersion forces will start working. And in that case, once the attractive dispersion forces start working, these particles may fuse with each other, may form aggregate. But the since formation of this uh, double layer, but we see these particles do not get closer because this diffused layer, so it is at the larger distances, also contains diffused layers up to two colloidal particles. If they are in one colloidal solution, will also have same charges, and they will repel, and they will still be separated. They will not get closer to each other. So when particles possess double layer, the overall effect is that particles repel each other at large separations, and this repulsion prevents their close approach. They remain dispersed, and the colloid is stabilized. The addition of more electrolytes to salt suppresses the diffused layer and reduces the zeta potential. So if you add more and more, so if you increase the concentration of the electrolyte solution, what happens? The diffuse layer is suppressed, it gets destroyed, and once the diffuse layer gets destroyed, the zeta potential is also reduced. The zeta potential is what is also a negative potential, as you've seen here in this case. The zeta potential is also a negative potential in this case. If the colloidal particle positive, it will be positive. The zeta potential is having certain negative value as shown here in this case. So the minus 100 is shown in this case. This value also has certain negative value. 0 is here. So zeta potential, value of zeta potential will reduce, and if the value of zeta potential will reduce, means the negatively charged particles, their charges will reduce, and their charges will reduce, means these particles will now they get aggregated. So the addition of more electrons suppresses diffuse layer and reduces the zeta potential, and this decreases the electric repulsion between the particles. As the zeta potential decreases, the electric repulsion between the particles, the colloidal particles, will also reduce to a large extent, and the colloidal particles will form aggregate, and thus they will precipitate. That is why colloid is particularly sensitive to oppositely charged ions, and this will mostly happen if the counter ions will move, they will go further. And so suppression, how this suppression is the addition of the large quantity of electrolyte suppressed with the diffuse layer. You can think about this. Now let us talk about the electrophoresis. So electrophoresis is what? It's a movement of colloidal particles under an applied electric potential. Under an applied electric potential or an electric field, movement of charged particle is called electrophoresis, and this charged particle in the case of colloidal solution is the colloidal particles. And these colloidal particles do have certain charges, whether negative or positive. And so what we know, the electrophoresis experiment is used to find out the nature of the charge on the colloidal particles. And so if we created an electric field, what we do, the apparatus contains an U tube, and both the arms of this tube contains two electrodes, so two platinum electrodes. And these two platinum electrodes behave as anode, so we connect it to battery, so we give different potentials. So the positive potential and the negative potential, once under colloidal solution, so this colloidal solution, you see, went through the reservoir, and this colloidal solution contains some colloidal particles. And initial level it was to here, but finally what happens, as you soon as this electric field is generated, this negative, the particles are negatively charged, they will start moving towards the anode, get attracted to anode, and so these charged particles, you can see here, it goes down their position. The water, this is the dispersion medium. So what we see actually is this kind of solution. So initially, suppose this is the colloidal solution, and this is positive electrode and negative electrode. It's fine, just position is changed. This was negative, right, left side negative or right side positive. In this figure, in this case, positive side is on the left side and negative side is on the right side. And so these colloidal particles are supposed to be negatively charged. So they will get attracted towards the positive charge towards anode, and so they will start moving towards this. We also see that the dispersion medium, this also moves to a certain extent, and this is what we call deionized water here. And so this kind of movement we observe, and if based on that we also find out what is the nature of the colloidal particles. So thus the existence of charge on colloidal particles is confirmed by electrophoresis experiment. The apparatus consists of a tube with two platinum electrodes in each limb. There are two limbs, two arms, and each contains one platinum electrode. When an electric potential is applied across two platinum electrodes dipped in colloidal solution, the colloidal particle moves towards one electrode according to the type of charge they carry. So what type of charge they carry, according to that, they move towards a particular direction. So if the particle accumulates near negative charged electrodes, it means the particle must be positively charged, and so the colloid contains positive charge. In that case, one can infer. And if the small particles accumulate near the positive charge electrode or the positive electrode, it means this particle, the colloidal particle, contains they carry negative charge, and that is why they get attracted to positive electrode, or they move towards the positive electrode. And when, so this is what one can infer. Yeah. So when electrophoresis, that is, what does it mean? It is the movement of particles, charged particles, is prevented by some means. It is observed that the dispersion medium begins to move in electric field, and this dispersion medium also begins to move in electric field, and this phenomenon is termed electroosmosis. And why this dispersion medium also begins to move in the electric field? Because this dispersion medium also contains certain ions because of the self ionization of water, or it also contains certain electrolytes in certain concentration. So when the initially if the colloidal particles are allowed to move, The colloidal particles, they are having larger charge, bigger in size, so they will start moving first. But if you stop the movement of these particles, what will happen? The smaller particles will now start moving with the smaller charge, and this process is called electroosmosis. So osmosis in presence of electric field is what? Electroosmosis. Let's now study about the coagulation or precipitation. So we have seen if you add the electrolyte after beyond a certain concentration, what we see, the colloidal particles, they get precipitated. So this precipitation, this process of precipitation is all called coagulation, or also it is also called flocculation. And this precipitation, coagulation or flocculation is what? It is the settling of the colloidal particles. When the colloidal particles start getting settled, this is the process is called coagulation, flocculation or precipitation. And there are different methods one can do for the used for the coagulation of lyophobic and lyophilic salts. So the due to similar charges, colloidal particles repel one another, and this is what we know, and cannot combine to form larger particles. Thus, colloid gets stability. And because of the charge they carry, similar charge they carry, with same nature of charge they carry, they repel each other. They do not form large particles. They do not combine each other. So they do not get settled. They do, and the colloid gets stability. However, if the charge on colloidal particles is destroyed by any other means, they get nearer to each other, so they get closer to each other to form aggregates, or and this formation of aggregates is also called coagulates. So they form aggregates or they form coagulates and settle down under force of gravity. And the settling down of the colloidal particles under the force of gravity, once their charge is removed, is called coagulation, flocculation, or precipitation. And this precipitation of sol as well, one can say, because what we are studying here is the sol only. The dispersed phase is in solid state and the dispersion medium is a liquid. The coagulation of lyophobic salts can be carried out in the following ways. The first is the by electrophoresis. The electrophoresis, what this thing we have just seen, what is electrophoresis? The colloidal particles move towards the opposite charged electrodes. They get discharged and get precipitated. Once they reach to the opposite charge electrode, there also the momentum is that these electrodes, we know the ions, the electrons also move. Because of that, they also either they if they are negatively charged, they remove the ions, they give up the electrons, they become neutral. As they are positively charged, they accept electrons and they become neutral, so they lose their charge and get precipitated there. The another way of coagulating lyophobic salts, these are all the methods for the lyophobic salts. For the lyophilic salts, we will see what one can get, by what method one can coagulate lyophilic salts. So another way is by mixing two oppositely charged salts. And by mixing two opposite, and these methods of coagulation, it also tells you that if you want to form a stable sol or a stable colloid, what things you should avoid. So you should avoid mixing two oppositely charged salts. And if the two oppositely charged, because if the two oppositely charged salts are mixed together, this oppositely charged salts, or if they are mixed in almost equal proportions, they neutralize each other. So they will neutralize each other charges and get partially or completely precipitated. And when they get partially or completely precipitated, that means this is what is the coagulation. For example, mixing of hydrated ferric oxide, and we have seen hydrated ferric oxide is what? The FeOH thrice effectively, it's a positive salt, and arsenious sulfide, which is a negative salt. We have seen that metal sulfides usually form negative salts. If we mix them in equal proportion, they will precipitate out. They salt brings them in the precipitated form. So they will, if you mix them in the equal proportion, they will precipitate each other. And this type of coagulation is called mutual coagulation. Means because of the positive salt, negative charge salt is coagulated, or because of the negative salt, positive salt is coagulated. And thus this kind of coagulation is called mutual coagulation. Or one can also call mutual precipitation. And this is because of the mixing of two oppositely charged salts together in almost equal proportion. Third method of the coagulating lyophobic salts is the by boiling. So when a salt is boiled, the adsorbed layer is disturbed due to increased collision with the molecules of the dispersion medium. So the adsorbed layer that is there in the adsorbed charge layer is disturbed due to the collision with the molecules of the dispersion medium. Once you start heating the colloidal solution, dispersion medium particles of dispersion medium they will absorb energy and the kinetic energy will increase. And thus the frequency and energy of collision will increase, and because of the frequency and energy of the collision, what will happen? The adsorbed layer will be disturbed, adsorbed layer will be kicked out from there, and thus the charge on the particles will be destroyed. And because of that, this what will happen? They ultimately settle down, they ultimately form precipitate, they ultimately get aggregated and they form precipitate. The persistent dialysis also leads to coagulation of the lyophobic salts. So what happens on prolonged dialysis, traces of electrolytes present in the salt are removed almost completely. So that whatever the electrolytes that are also required for the formation of electrical double layer, those electrolytes will also be removed, and thus the electrical double layer will be destroyed and the colloid become unstable and untimely coagulate. We can also coagulate this lyophobic salts by adding electrolytes, means the excess of electrolytes also leads to coagulation of the salt. So when excess of electrolyte is added, and that thing we have already seen, it also destroyed the diffuse layer, and so uh, precipitation of the colloidal particles happen with the addition of the excess of electrolyte. So when excess of electrolyte is added, the colloidal particles are precipitated. The reason is that colloids interact with ions carrying charges opposite to that present on themselves, and this cause neutralization leading to their coagulation. The ion responsible for neutralization of charge on particles is called coagulating ion, and some means there are ions which leads to the neutralization of the charge on the particle, and those ions are called coagulating ion. A negative ion causes the precipitation of positively charged salt, and a positive ion is responsible for the coagulation of negatively charged salt, and that is why they neutralize each other. So positive ion, if you add, it can neutralize the negatively charged salt, and if you neutralize the negatively charged salt because of the interaction between the absorbed particle on the surface and that ion that is there into the that has come from the electrolyte, and so they get neutralized, and once the salt gets neutralized it will get precipitated. Let us now read about this Hardy Sudje rule. Hardy Sudje rule, what it tells about, it talks about the coagulation capacity of different ions. So different ions, as we have seen that just we have studied about the adding of electrolytes. So by adding electrolytes, maybe positive ions. So if there are many electrolytes which contains positive ions, and there are many electrolytes which also contain negative ions. So if you want to neutralize the positive charge salts, you have to add negative charge electrolytes containing negative charge. So negatively charged ions will be coagulating ion. So what will be the effect of this negatively charged, different negatively charged coagulating ion? What is their power, their potential to coagulate the salt is what we understand, we study in Hardy-Sudje rule. So Hardy-Sudje rule tells the coagulating capacity of an electrolyte depends upon the valency of the ion responsible for causing coagulation. Means the valency. What is the valency? Means what is the charge on the ion? Whether it is positive charge, so how much positive charge on that ion is there, or if it is the ion is negatively charged, how much negative charge it is having, and depending if the charge is more, means the valence is more, the efficacy of ion to neutralize the colloid will be more. The efficacy, the efficiency, the power of that ion will be more, and that is what we study. It's called the Hardy-Sudje rule. So we have seen that the ion responsible for causing coagulation is the one that carries a charge opposite to that present on colloidal solution, the colloidal particles mostly. So the for instance, because colloidal solution will be electrically neutral, so I should have said colloidal particles or the dispersed phase particles or the particles of dispersed phase. So for instance, a positively charged salt gets coagulated by negatively charged ions of the added electrolyte. So the positively charged salt will be neutralized by or the coagulated by negatively charged ion, or the negatively charged colloid will be neutralized by positively charged ion of the added electrolyte. And the greater the valency of the positively charged ion of the electrolyte added to the colloidal solution, the faster is the coagulation of the colloidal solution. This is called Hardy-Sujci rule. Means that if the greater is the valency of the opposite charge ions, the greater is the charge on that ion, greater will be its coagulation power, and that faster means the faster will be the coagulation, and that is what we call the Hardy-Sujci rule. That is pronounced as Hardy-Sujci rule. Hardy-Sujci rule. For example, the coagulation power of different cations of for coagulating a negatively charged salt of arsenic sulfide follows this order. So if you look at these three ions, aluminium 3 plus ion, barium 2 plus ion, and sodium 1 plus ion. What is the valency of aluminium 3 plus ion? Its valency is highest, 3 plus charge is there. Then barium 2 plus ion is having 2 plus charge, and sodium ion having 1 plus charge. And so their power to mm, coagulate negatively charged arsenic sulfide salt will be in this order. The aluminium ion having 3 plus charge, its valency is most, so it is having highest power, so its efficiency, its efficacy will be most. Then the barium 2 plus ion having 2 plus charge, and least will be for the sodium ion, which is having only one positive charge, so its valency is 1 only. Similarly, for the coagulation of positively charged salt, we require negative charge ions, and thus one can also follow to get the same order for negative charge ions as well. So for the positive charge salts such as FeOH thrice, the ferric hydroxide salt, the coagulating power of different anions follow this order, and what we see, this is the ferricyanide, and it's a, it has 4 negative charge, and this 4 efficient 6 4 negative charge, and so it is having 4 negative charge, so its efficacy will be most. Then phosphate ion, which is having 3 minus charge, so its efficacy will be then its power will be, after that this will be having highest power, and then the sulfate with 2 negative charge, and least will be the chloride. So these ions follow this order, because and this order is because of the charge they carry on their ions. So this is having 4 negative charge, this is having 3 negative, this is having 2 negative, this one is having 1 negative charge, and so valency also changes accordingly. This is having highest valency, then this one, and this one. And so based on the valency, the ion is having higher valency, so its power of the coagulation will be more, and this is what Hardy-Sujci rule. We'll see other points about the coagulation and flocculation, and there's other points about this in the next class, and we will wrap this chapter in the next class.